Well, it's funny because remember that NaCl stuff, that table salt that we all like so much? Well, the thing is, it's actually made from Na and Cl, and Na is a reactive metal, so if you put that in water, it'll start to like sizzle and boil essentially, and Cl is actually a poison gas. So I wonder, how does our body break this apart? Does it like, do we have chlorine just kind of like in our body somewhere? Like, what's going on here? Well, anyway, that's the point. So it's weird because when you combine these two elements, they turn into something that you can actually just eat. What this essentially means is that the properties of elements by themselves are going to be completely different from the properties of the compounds that they would make. And we have three kinds of chemical bonds. We have the ionic bonds, we have covalent bonds, and we have metallic bonds. So ionic bonds work by donating electrons, giving electrons back and forth. So donating electrons. This is essentially what's happening right here. This guy, Na, is donating an electron to the Cl, and it's completing its electron shell and kind of trying to achieve the noble gas structure. So that's an ionic bond. Now the covalent bond is going to be through sharing electrons. So in a water molecule, for example, you would have the oxygen needs 2 electrons. The hydrogen has 1 electron, but it needs 1. And so they're all just kind of sort of share. The hydrogen is going to share 1 of its electrons. The oxygen is going to sort of take that, and then the hydrogen, so that's going to be the covalent bonds. And we have the metallic bonds, which is going to be a little bit different. It's going to be more like an electron sea, the sea of electrons. So instead of each molecule sharing just the electrons between itself, H's and O's sharing just between themselves, the electron sea, is the entire structure. Every molecule is sharing all the electrons with every other molecule as well, which makes it conductive. So that's why the metallic one is the electrons can go everywhere in the entire collection of all the molecules. They're all sharing all the electrons. It's crazy. As far as representing the elements on paper, we can do that by using molecular formulas. For example, a simple CH4 will do. So we know that we have 1 carbon and 4 hydrogen, but you could sort of make this a little bit more visual by drawing out the bonds like this. You can see single bonds with the hydrogens there. But we can also draw it in other ways. Like if you have a ball and stick, you can actually just get like actual physical balls and sticks, get the carbon in the middle and have a couple of smaller balls over here for the hydrogens. That's pretty cool. And remember the space filling ones that are kind of like in those weird little machines that you can kind of see, like those museums where they kind of have the little balls attached to the things and you kind of move them around in those things. So that's the space filling one. So this is kind of a couple different ways you can represent these compounds. All right, now let's take a look at that thing right there. That's a skeletal structure. So it'd be pretty helpful to know how to read that kind of stuff. So the first thing you want to know is you want to put the C's at every point of the chain. So let's fill in the whole chain with C's. We'll get a C there, then we have a C there, and then we're going to put a C in there, get the double thing with the O, and then you can put the C at the end. So you get the C kind of, it's going to be a whole chain of these C's all the way, these carbons. From there, we're just going to count how many bonds they have and add the number to complete how many they would need, which is 4. We've got 3, we got an H over here. This one already has 4. This one requires 3 H's. And I think that would be correct. Skeletal structures. One more time, if you didn't really see where those C's go, you put the C here, here, right here, and then here, because that would sort of complete your entire chain that's already been filled up. Okay, now this is a pretty important chart. We have atomic elements that we can find on the periodic table. I'll just mark 1, helium. The molecular elements, this one here I've marked in red because there's going to be a whole bunch of them we have to remember, right? One of them would be, for example, O2. There's just a whole bunch of molecular elements that we'd have to chart to remember that. The ionic compounds, these ones, they're relatively easier to sort of figure out because it's just about the pluses and minuses. So if you can figure out what the charges are, we're going to look more into the ionic compounds a little bit later. But then for the molecular compounds, again, there's going to be a couple of these that you might want to remember, like the acetic acid stuff, vinegar, and glucose and sugar and things like that. So there's going to be a couple. These are, you want to keep lists of all these compounds, the most common ones at least. Maybe remember a few of them. Let's talk about how to name the molecular compounds. Usually you would need to get a prefix, and then you would have the name, and then you would have an IDE at the end. So the prefixes are going to be things like mono, di, tri, so like carbon dioxide, dihydrogen oxide, those kinds of things. Ionic compounds are pretty easy to put together. You're going to need to have a metal and a non-metal. And let's see, so you would have something like aluminum, and then you would have an oxygen. Well, the key is to remember that aluminum is a 3+ charge, and the oxygen is a 2+ charge. And then, well, you're going to notice that this thing would need to move over there, and this 3 would need to move over here. There's those superscripts are going to switch to the subscripts of the other compound. So basically what's going to happen is Al, and then you get a 2 right here, and then you're just going to get your O and a 3 right here, and that's going to be your ionic compound, aluminum oxide. How did I know the name of that? Well, because it's a binary ionic compound. Binary means that there's two elements in there. So if there's only 2 elements in the compound, then you can use the binary ionic naming system. That would be the metal plus the non-metal plus an IDE at the end. So for something like KCl, that would be potassium chloride. So this binary ionic naming system is actually very easy to understand. The polyatomic oxyions become a little bit more complicated, because now we would have a metal plus an ion. So that means you're going to have more than 2 elements in there. That would be something more like calcium sulfite and calcium sulfate. You'll notice that there's 3 elements in this compound. And over here you would have the ions. You can even put parentheses around those. So this is going to be calcium sulfite, and this is calcium sulfate. And the difference is that the sulfites are just smaller, and the sulfates are bigger. I guess the sulfate, they ate the sulfites. I don't know. Well, we can actually go one past the ites and eights by saying, what if we had like a SO5 in there? Then this would be persulfate. So here you would just take your 8, but you'd need to add 1 oxygen. In order to get the persulfate, SO5, you took your sulfate and added 1 oxygen. In order to get the SO2, this is going to be a hypo. So a hyposulfate, you're losing one of those oxygens. So you're taking the ite and you're going to subtract 1 oxygen. So the ite minus an oxygen gives you the hyposulfite, and the 8 plus 1 oxygen gives you the persulfate. Another naming system for some of the ionic compounds that have multiple charge numbers would be the metallic charge system. This is called the systematic method of nomenclature. So let's say we have Fe2+, comparing that with Fe3+. These are 2 different charges that you could give to this iron. So we would call it iron 2 and iron 3. And over here, this one would be called ferrous, if we were to call it a more interesting name. And this one would be called ferric. So this one would be the least, and this one would have the most number of charges, of course, here. So ferric is the highest, and ferrous is the lowest. By the way, if something has more than 2 different charge states, then you just want to use the Roman numerals, because I think there's only these 2 names. Well, remember that Heisenberg boiled some bodies in hydrofluoric acid? Yeah, let's start naming those acids. Those are pretty cool. You're going to have hydro dash non-metallic acid. So, for example, we had the HF, which was hydrofluoric acid. And that's going to be binary. Again, we only have 2 elements in that acid. Now for the oxyacids, these are going to be acids that contain some oxygens in them as well. So first we'll start with saying like a non-metal. And then let's see, you could have either the ites or the ates, right? Because you have a sulfite or a sulfate. And if it's an ite, then it's going to be an ose acid. And if it was an ate, like a sulfate, then it would be an ic acid. And let's see, so we could say on the bottom here, so HSO4, this is going to be sulfate, but it's going to be turned into a sulfuric acid. Sulfuric acid. And notice one important thing, we dropped the hydro part. So we just start straight with the non-metal if we have a big ion on the right side. And for the top, let's say it was HSO3. Here again, we're dropping the hydro part and we're going straight to the non-metal and we're calling it sulfurous acid because it was an ite. Let's take a quick peek at these things called hydrates. They contain H2Os. So you would have a compound plus a prefix plus a hydrate. Let's see, we would have a CuSO4 dotted with 5 H2Os. In order to name this, you're going to name the compound first, so copper 2 sulfate. Copper 2, because sulfate has a charge of 2, so you need copper 2 sulfate. And then you're going to go into the prefix, so you have 5. That's going to be a pentahydrate. Alright, so it's basically compound and then the space, and you can prefix plus the hydrate right there. Now for my favorite compounds, we have hydrocarbons. So that's going to be like C2H6, hydro and carbon. So there's 3 kinds. You're going to have the anes, you're going to have the enes, and you're going to have the ines. Obviously the anes have an A, the enes have an E, and the ines have a Y. That's kind of the order they come in the alphabet too. These things just have a single carbon bond. These things, so like for example C-C. Over here these would have a double bond somewhere, a double C bond somewhere in there. You get C-C right there. And then for the Y's you would have a triple C bond somewhere in that compound. Let's take a little detour and try to figure out from the empirical formula, how could we use the molecular mass of the full compound to figure out what the molecular formula would be? Well, let's say we had CH as the empirical formula. Keep in mind, the empirical formula is the simplest ratio of whole numbers. And this is very much relative within the compound. The molecular formula is going to be more of the complete formula. So like, while this thing is 1-to-1, you could see how there's 1 C and 1 H. The molecular formula is going to be complete. How many C's and how many H's do we actually have? I know it's a 1-to-1 ratio because the empirical formula tells me, but like, do we have 3 C's and 3 H's? Do we have 6 C's and 6 H's? How many C's and how many H's? That's the real molecular formula. So this is the simplest ratio, and that one's the complete one. Let's say we looked at the periodic table and we saw that carbon plus the hydrogen gives us a 13 grams per mole conversion rate. But over here, the full compound molecular mass, that happens to be given to us. Okay, they tell us that it's 78 grams per mole. That is the molecular mass. So with that in mind, let's see how many times does 13 go into 78? Well, it's going to be 6 times. So over here we know that it's C6H6 because we just multiply the empirical formula by 6. Now it's really important that we know how to balance chemical equations. So let's take a combustion reaction and make an equation. There would be something like taking a substance and combining it with some O2, the oxygen there. And then that would create carbon dioxide plus H2O. If there isn't enough oxygen, sometimes this stuff can make COs, carbon monoxide, or even just pure C, carbon emissions. Now, in order to balance this, let's say you did a whole bunch of calculations and you got some strange fraction. Here's the point, is that if you try to balance the equation, try to keep it in fraction form. So you can keep it in fraction form. You can just multiply everything by the denominator at the end. And this is the key fraction. It just might help a little bit with balancing equations a little faster. Remember that hydrocarbons are essentially just gasoline, but if we replace one of those H's with some kind of group of elements, then we're going to get some other stuff. So for example, the amines, alcohols, the ethers, aldehydes, ketones, esters, and the carboxylic acids. So for the amines, let's take the hydrocarbon and we're going to go ahead and switch one of the H's out, and we're just going to put in this group NH2, and then we're going to call that at the end, it's going to be like an amine at the end. And for the next one, alcohol, take that hydrocarbon, switch one of those H's to an OH, and we'll end that with an OL, like alcohol. The ethers are going to be an R-O, and then there's another hydrocarbon to the right. So there's actually two hydrocarbons. This is oxygen right in the middle, and these are going to be, there's going to be some sort of an oxy word in the middle of the ether. Okay, and for the aldehydes, we would have our hydrocarbon, and then we have a CHO, and this is going to be ending with an AL. The ketones have R, CO, and another R. Remember that they end in the ons. And again, these are just kind of to recognize these a little bit. We have the R, COO, and another R. A little bit similar there. These are called the anoates. And the R-COOH. This is going to be an oic acid. Just in case you happen to see like the formula and you notice, hey, wait, there's a CHO in there, and then there's a whole bunch of hydrocarbons. Oh, I know that's going to be an aldehyde. And then maybe they'll even give you the name of it. And so you might be able to recognize it from there. So this is just kind of an interesting little table to try to remember. So, crazy stuff.